Welcome back! Mr. Pike, where'd all your hair go? That was a year ago, crazies. Okay, so in this video, we're going to be talking about related rates. So essentially, up to this point in calculus, we have done derivatives. The derivatives are the rate of change of the original function at any given instant, right? So the derivative represents the slope of the original function. That's why I keep drilling into y'all's heads. So with related rates, things are not, I don't want to word this. Should have thought about this before I started speaking. Anyways, things change with respect to others. So let me just start by my first example here. So if I have a balloon, right, balloon, as I blow it up, there's things that are changing here. The volume is increasing as I blow it up. The surface area is also increasing. The radius is increasing, which means the diameter is also increasing. And as I blow it up, if I assume that this is a sphere or something like that, the bigger it gets, the rate of volume is still increasing at the same rate, assuming that I can blow air at a constant rate. So the volume is increasing at a constant rate. But the radius is changing at different rates depending on how big the balloon is. So let's let all the air out, right? So at the very beginning, the radius is pretty small, but within the first breath, notice how the radius increases rapidly and then it starts to slow down a little bit. So, right, so it goes from this big to about this big in maybe half a second, but maybe the other half a second or whatever, it only goes to about that big. So the radius slows down as it grows and grows and grows. So that is as I am blowing air into the balloon, as I am increasing the volume. As I am increasing the volume, things are going up. The measurements are getting bigger, right? I'm adding more to it. But as I decrease the volume, right, everything is going down. The dimensions are getting smaller, so things are decreasing. They're getting smaller. So this kind of idea of things getting bigger, things getting smaller, how the change in the volume relates to the change in the radius or the change in the surface area is everything to do with related rates. That is pretty much what we're going to be focusing on with this. So how one variable changes with respect to another, and how they both maybe change with respect to time. Because I can't just like blow it up and instantly it's that big or whatever, right? It takes some time to get there. So this is nice in the sense that it tells us when things are happening as well. So, that trash out of here. Often, it is how two variables are changing with respect to time, but there for sure could be more than that. Okay, so let's just jump right in. The variables x and y are both differentiable functions, which means they are continuous of t. So they are functions of time. So this is like y of t, x of t, so on and so forth. But we're not going to worry about writing it like that. Okay. Related by the equation y equals x minus 4x squared, find dy dt when x equals 1, given that dx dt equals 3. And notice with these, the derivatives are done with respect to time. So this is the change in y with respect to time, so where it's changing vertically with respect to time, versus where it is changing horizontally with respect to time, at the specific instant that x equals 1. Because this is a graph of a parabola, right? If I have x minus 4x squared is something like this, where I have an x-intercept at 0 and positive 1/4. All right, we'll get to that in just a little bit. So what I want to do first is just kind of slowly take you through how we are going to do the derivative with respect to time. And this all goes back to the chain rule. So if I want to do the derivative of this equation, d over dt of this equation, well, kind of like what we were just doing, if I did the derivative of y with respect to x, it came out y prime, or dy dx. So similarly here, if I'm doing the derivative of y with respect to time, it's just dy dt. Right? So the weird thing that you guys are going to get caught up on maybe is now when I get to x, right? Because before we were doing the derivative of x with respect to x, but now I'm doing the derivative of x with respect to time. which kind of like dy dt, I don't know how it simplifies. I can't simplify dx dt either, so it's going to stay dx dt. Then with this one, I'm going to have to do the chain rule because I kind of have the x inside the quadratic altogether. So I'll have minus 8x, and then the derivative of the inside will be another dx dt. Once I have this set up, it's pretty straightforward that I can plug in 3, I can plug in 1, and I'm looking for dy dt. So dy dt is equal to 3 minus 8 times 1 times 3, which comes out as negative 21. They don't really give us any units in this one. It's the change in y over the change in time. They don't give any units for time. They don't give any units for distance or anything like that here, so I'm not going to worry about units on this one. One other thing I want to kind of point out to you guys is it's similar to what we've been doing before. It's just now with respect to time. Because if I take this and I do dy dt over dx dt, right, that would simplify to be dy dx, which is what we've been doing up to this point. So if I divide those two numbers, right, dy dt is negative 21, dx dt is 3, negative 21 over 3 is negative 7. What is that? Negative 7. Now I bet you 20 bucks, only 20 though, sometimes I make mistakes, is that if I find dy dx when x equals 1, I bet that's going to come out to be negative 7. So let's see. If I take my quadratic here and I do y prime equals 1 minus 8x, this is differentiating with respect to x now, right? Then y prime at 1 be 1 minus 8 would hey-oh is negative 7. Magical. But none of this is really anything you need to worry about right now, because I just want you guys to understand how to do this differentiation with respect to time. This is not going to be the majority of your problems with respect to x and y. The majority of your problems are going to be something like example 2 here, where it's something actually happening in real life, right? My physics professor in college he was really excited when he was talking about this idea. He had like a monkey hanging off the roof by a string or something, fake monkey. And then he had this cannon that shot tennis balls, and he adjusted his angle appropriately. He adjusted the speed with which the tennis ball shot out, and he pressed a button. He would go boop, and the cannon would fire a ball which has this sort of motion. And based on the rates of changes of everything, he was able to calculate that the ball fired at the same time the monkey was dropped, and he was able to hit the ball out of the monkey out of midair. This was from like 50 feet away or something like that. So he always got really excited about it. And it's kind of interesting, but he always got more excited than I did about that stuff. But I guess you probably feel the same way, huh? Calculus is super cool! And you're like, oh, yeah, calculus is cool, man. Okay, anyways, let's go. Got a lot to do. So an inverted cone with water is draining. So I have this cone filled with wawa, right? There's a bunch of water in there, and it is draining out. So it is leaking out the bottom of this thing. So draining at a constant rate of 20 centimeters cubed per second. So that means my change in volume versus my change in time is draining. So it's coming out of this thing. So it would be negative 20 centimeters cubed per second. All right, so that's the first part. The height is 5 times as large as the radius, so h equals 5r. When the radius is 9 centimeters, how fast is the radius changing? So this is talking about what is the rate of the change versus time of the radius. So I'm looking for dr dt equals what when the radius equals 9 centimeters. Okay, so now I need to think. I need a relationship that I can relate volume with my radius. So the change in those two things. Well, my volume formula of a cone, since I have a cone, is 1/3, yikes, pi r squared h. Well, there's an h in there too, because that's an issue, right? So if I take the derivative here, it's just dv dt. But if I take the derivative here, that's dh dt, which I don't know how fast the radius is, or the height is changing. Because really all I need is dr dt. Well, nice thing, right? They gave us this relationship. This isn't true for every cone, so don't assume it's true for every cone. It's not. Snot, nose, snot. Okay, sorry. So what I can do is with that relationship, I can say that the height is 5 times the radius, which now I have the volume in terms of just the radius. So the volume is 5/3 pi r cubed, if I kind of rewrite that to make finding my derivative easier. So now if I do the derivative, dv dt, the change of volume with change of time, right? So I'm doing d over dt of this stuff, equals, I will have to apply the chain rule here because I have like an r cubed, and then within that I have an r, so I'll bring down the 3, so 3r squared. So 5/3 pi times 3r squared, that's at 2 times dr dt. The 3's will divide out, and I can plug in what I know now. So dv dt is -20, 5 pi times r, which is 9, squared dr dt. And then we get to use a calculator. Oh, come on, mouse. Come onto this screen. I have 2 screens here, and it's confusing. I don't know what's going on. There's my calculator. Okay, so with this, let's see if I can get it to work. I have -20. Come on, let me type. Let me type. Oh, do I have to be on the screen? That's stupid. All right, so -20 divided by 5 times pi times 9 squared. All right, make sure you have your parentheses around that, otherwise it will not come out. So now the other thing here is that you need to go to, I want you to go to 4 numbers. So I'm going to write the answer here as dv dt, sorry, not dv dt, no! dr dt equals -0.0157 1. I am going to, this is called truncating the number. I'm just going to stop on the 4th digit. 5 minutes, we'll hear another one. I'm going to stop on the 4th digit because AP Calculus, they really only ask you for, I guess, 3 numbers. So they are only looking for the 157. But in the past, I've been told that if you say you have like a 9 or something like that, and you forgot to round this 7 into an 8, and you only went to 3 places, you would lose the point. However, students that just truncate, that just stop, don't even round or anything, if you go more accurate, so if you go 1 place extra, and you don't do any rounding or anything, you're good. You're fine. You can be more accurate, you just can't be less accurate, is their way of explaining how they grade. Okay, so there's our number. Now we need to think about what this represents. This represents the change in the radius versus the change in time. So change in radius versus change in time, which means this is changing -0.01571 centimeters every second. Right, so that is using the same rates that they're getting to. And if it helps, right, dv dt is centimeters cubed per second. R squared is centimeters squared. So if I'm dividing over that r squared, I'm dividing out the centimeters squared. So that gets me to centimeters per second as well, if it helps you to think about the units. Grading-wise, you will get 1 point for the derivation, you will get 1 point for an answer, and you will actually get a point for your units. So be careful. Make sure you guys put your units if we are dealing with units. Okay, so that was how fast the radius is changing. Now we need to go through and do how fast the height is changing. 2 ways of doing this. Option number 1, we already did dr dt, and I have a relationship between h and r. This is the way I would do it if it were me. especially since I already did this problem. H equals 5r. If I do the derivative, then dh dt equals 5 dr dt. So all I have to do, let me do it, is take my previous answer, multiply it by 5, and press enter. So dh dt equals negative 0.07859. 859 centimeters per second. All right, so I'm just truncating. I'm stopping after I write the fourth number that is important. Okay, that's one way of doing it, right? And that was just using the relationship to be able to get there. That is the way I would highly encourage you to do it if you've already done all the work. The other way is kind of by the same logic, right? We can use the fact that h equals 5r, so then the radius is the height divided by 5. Substitute that into my volume equation, so I have 1/3 pi h over 5 squared h. Then everything is in terms of h, and you can do the same thing. Okay, moving on. We are on number 2 after 16 minutes. Oh my goodness. I'm reworking this video because it was bad. I made mistakes. I didn't do things the easy way. I think it was like 48 minutes last time. So let's beat it. Let's beat our record. All right, here we go. A balloon's volume is increasing at a rate of this, so that means dV dt is positive 5 inches cubed per minute. Find the rate of the change of the radius when the radius is 6 inches. So I'm looking for dr dt equals what when the radius equals 6 inches. The volume of a balloon, we're going to assume it's a spherical balloon, is 4/3 pi r cubed. Move that over a little bit. Okay. So now I can do the derivative. So if I bring down the 3 for the r cubed, that'll be 3r squared and then times dr dt. So that will take care of the 3 that I have right there. So I have 4 pi r squared dr dt. Plug in some numbers, so 5 equals 4 pi. R is 6 at this instant, dr dt, which we can do some math. 5 divided by 4 pi times 36. I can't get it. 0.01105 inches per minute. All right, that one was not so bad. Okie day. Here we go. Monkey being blasted into space with a velocity of 350 feet per second. The observers are standing 7,000 feet away from the launch pad. How fast is the angle of elevation changing when the monkey is 4,000 feet vertical? Okay, so I like to draw a picture to help me think about these things. So I have a monkey. He's got a helmet, whatever helmets look like, and he is being blasted upwards in a straight line, I assume, at a rate of 350 feet per second. So that is my height. I also have observers 7,000 feet away, and they are watching Mr. Monkey go into space. We're assuming that Mr. Monkey might come back. Maybe, maybe not. We don't know. Okay, but the change in height, he's going up, is 350 feet per second. So there are a few things changing here, right? The height is changing. This distance, if I needed it, is actually changing, right? That should be getting larger. This distance is not changing. We're going to assume that those people are going to stay 7,000 feet away the entirety of the launch. They are not going to move. No step forward, no step backwards. Do not move! Also, the angle of elevation is changing, right? So it's much smaller than it is up there. Okay. Now, it's asking specifically when the monkey is 4,000 feet vertical, how fast the angle of elevation is changing. So I'm saying d theta dt equals what when the height is 4,000? So I need a relationship here, especially since I'm looking for d theta dt. I need a relationship that I can use my angle in. So thinking about this, I know this rate of change. I know this is a constant. And this should be a right angle. I'm going to assume that it goes straight up. The Earth isn't moving or anything like that. Everything's just going straight up. Yep, perfect world, perfect imaginary world. But that should be a right angle as long as I'm going straight up. So what I can do is say then that tangent of theta equals the height over 7,000, such that now when I do my derivative, you can see that, right? Yeah. My derivative is secant squared d theta dt equals 1 over 7,000 dh dt. So now I have d theta dt is what I'm trying to find. I have dh dt. So really, I just need to figure out how to evaluate this. Well, remember for me that secant squared is 1 over cosine squared. Right? So if I want to get rid of this 1 over cosine squared, the secant squared, and I multiply it to the other side, it's just cosine squared. So I'm going to say d theta dt equals 1 over 7,000. dh dt is 350 cosine squared of theta. So now, how do I figure out cosine? Well, there's a few things you can do. One, you can find the angle, which that's the way I used to teach this. I don't do that anymore because we don't need it. Two, I can figure out the actual value of cosine. Much easier. Because this side is 4,000, right? It's asking about the instant when that side is 4,000. So then my hypotenuse here would be the square root of 7,000 squared plus 4,000 squared. If you recognize that you can do this as 7 squared plus 4 squared, you can do that too. You can do that. I don't want to confuse y'all, so I'm not going to get there. But if you recognize that it's just the ratio of the sides, then you can do that. That's probably the way I would do that. Okay, but cosine then is adjacent over hypotenuse, so 7,000 over that square root, 7,000 squared plus 4,000 squared, squared. Since it was cosine squared, I need that squared on the outside. So then just be careful typing it in. So I have 1 over 7,000 times 350 times 7,000 over the square root of 7,000 squared plus 4,000 squared. All that junk squared. And there I go. So my change in the angle, I'm just going to make all this junk smaller. Whoop. Okay, sure, why not? So my d theta dt is 0.03769 radians per second. In calculus, we are always going to be talking about angles in radians. That is all I am ever going to do. So everything will be in radians. Okay, moving on. Alrighty. Plane flying horizontally at an altitude of 1 mile and a speed of 500 passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So with this one, I have a radar and I have a plane going this direction. Right? And it's telling me that the speed is 500 miles per hour. So let's just call this side P. So dP dt equals 500 miles per hour. And I'm talking about the instant that the plane is 2 miles away from the station. So just be careful on this, because the distance from the plane to the radar station is this distance right here. That's the distance we're talking about. Okay, horizontally at an altitude of 1 mile. So this altitude, we're assuming the plane doesn't go up, doesn't go down at all as it's flying. it's staying that constant 1 mile above the radar station the entire time. So I'm trying to find, I'm going to call this side length d. It's trying to find the rate at which the distance from the plane is increasing. So it's trying to talk about how this distance is increasing as the plane is flying this direction, right? So it should be positive. Both of these are getting bigger as they go. So let's see. If I'm trying to look for d dt equals what when p equals 2, oh sorry, d equals 2, then what I can do is I can come up with like Pythagorean theorem and say 1 squared plus p squared equals d squared. All right, so now if I do my derivative, and the reason that I can put the 1 is because this is a constant. That's never going to change. The change is happening with the p and the d distance. The p is changing, the d is changing. So those are the numbers that I need to do the derivative with. So if I do my derivative, this becomes 0, right? I'll lose that term. So I have 2p dp dt equals 2d d dt. The 2's will divide out, so I lose those. So really I have p, which at this time, if I have 1, 2, then this is the square root of 3 by Pythagorean theorem. So I have root 3 times 500 equals the distance, so 2 times d dt. So it's really just root 3 times 500, so 500. Let me type 5. Come on. Come on. 500 root 3 divided by 2. So 433 0 1 2 7 miles per hour. And that is just at that instant. Yeah, I don't see anything wrong. That number is just weird to me. I guess it's because it's a y direction here. Interesting. Okay. All right. Snowball melts so the surface area decreases at a rate of 1 centimeter squared per minute. So I'm talking about the surface area. It's being -1 centimeters squared per minute. Find the rate at which the diameter decreases when the diameter is 10 centimeters. So the change in the diameter over the change in time equals what? When d equals 10. Right, and the diameter is 2 times the radius. So the radius is the diameter divided by 2 is kind of what I will want to think of as I'm going through this. Because the surface area of a snowball, assuming that it's a perfect sphere, is 4 pi r squared. Ooh, no. Change in the surface area. Sorry, change in the surface area over the change in time. Yes, okay. So then I can do my derivative such that the change in the surface area over the change in time. I'm not going to do it yet, I'm lying. Boo! Okay. The reason I'm not going to do it yet is this is still in terms of r. So the surface area is 4 pi times d over 2 squared, which I will actually like to rewrite because 2 squared is 4, so this is really just pi times the diameter squared as the surface area, so that now if I do the derivative, the change in the surface area over the change in time is 2 pi times the current diameter times the change in diameter over the change in time. Okay, plug in numbers, -1, 2 pi times 10 d dt. So if I didn't have a calculator, this is a very good one to ask without a calculator, right? All I'm going to do is say the d dt equals -1 over 20 pi centimeters per minute, right? Which comes out as -1 divided by 20 pi. Please notice the parentheses as -0.01591 centimeters per minute. All right. I think all that showed up. Okay. Okay, now we get to some fun problems. I'm going to delete this, give myself a little bit more room. So I have a man that starts walking north at 4 feet per second from point P. So point P, man walking due north, 4 feet per second. I'm going to call that length A. Well, I'm going to call that M. This is the man. That's the man. 5 minutes later, a woman starts walking south at a rate of 5 feet per second from a point 500 feet due east of P. So if I'm due east, that just means I'm directly east. Here's a woman that goes due south. There is the woman. Here is the man. This distance is 500. At what rate are the people moving apart 15 minutes after the woman starts walking? So 15 minutes after the woman starts walking means that her distance, the woman at 15, would be, let's see, she's walking 5 feet every second. So 5 feet every second would mean she walks 300 feet per minute. She's walking for 15 minutes. Whoop, got the plus sign. So she walks 4,500 feet in that 15 minutes. The man, so now here's the thing, a man starts walking and then 5 minutes later a woman starts walking. So if the woman has been walking for 15 minutes, that means the man has been walking for 20 minutes. So the man at 20, he goes 4 feet per second, so that many every minute for 20 minutes would be 4,800 feet total. Okay. At what rate are the two people moving apart 15 minutes after the woman starts? So it's talking about this distance right there. Right, so I'm talking about that distance. And you can make this a big complicated problem if you want to, but the way that I prefer to look at this one is to make my own new triangle, because this distance is coming from, right, the man's plus the woman's length, right, those are both increasing, and then that 500. So this becomes a simple right triangle. So the total distance over here is like the man's plus the woman's rate. So I can set up Pythagorean theorem such that I have man plus woman squared. It's going to get out of the way of the calculator. Man plus woman squared plus 500 squared, because that's a constant, equals that distance squared. So that now if I do the derivative, I have 2 times the man plus the woman distance times the derivative of them, so dm dt plus dw dt equals 2d dt. So like we said, the man's rate is, the man's distance at that time is 4,800, plus the woman's distance at that time is 4,500. dm dt is the rate of the man, so 4. dw dt is 5. And 2d, d is going to be the square root of 500 squared plus 4,800 plus 4,500 squared, right? Because it's this entire length squared plus this entire length squared. The square root of that is my hypotenuse. So I have square root 500 squared. Well, let's see what number that is, so I don't have to rewrite it again. 500, come on. 500 squared plus and maybe that's a nice number. Why you do that? Square root of my answer. No, that is not a nice number. Okay, so 8674 and 4 zeros. All right, so 8674 and 4 zeros, and then dt. The 2's will divide out, right? So I really just have, I just have to divide over that square root number. So I have 4800 plus 4500, right, times 4 plus 5, which is 9, divided by that number. So that should be dt equals 8.9870 feet per second, right? So this is just in feet. This is in feet per second. This is in feet per second. This is just in feet. So I'm dividing out the feet so that the rate stays in that feet per second rate. I don't have to convert those 4's and those 5's if you were thinking that I did. Okay, and that's all there is to that one. Kind of a pain in the butt, but that's where we are. All right, I think we got 2 more. Yeah. And the last one I know is easier. This is the last doozy of a one. Delete. Okay. And I hope you know that this isn't meant to be taken all in at once, right? So I'm teaching this over 2 days. This is a lot to take in all at once, but I want to be thorough in our video, so I'm sorry that it is going longer than most are. So 2 carts, A and B, are connected by a rope 39 feet long that passes over a pulley P. The point Q is on the floor 12 feet directly beneath P. Between the carts, cart A is being pulled away from Q, so then cart B is moving towards. So let's draw out our situation, right? So I have a point P, I have a point Q, such that the distance from P to Q is 12 feet. And then I have these carts, cart A, cart B, connected to both. And it is 39 feet long. So if I call this, I'm going to call this distance 1 and distance 2. Distance 1 plus distance 2 is 39. And it's telling me cart A, I'm going to call this A, and I'm going to call the other one B. Right, so that's just the distance that they represent. Okay, so A's distance was being pulled away at 2 feet per second, and his is increasing. So dA with respect to dt is positive 2 feet per second. You still see that? Oh, I'm sorry, I cut out the problem. Okay. And these notes are in the drive, so please pull them up, follow along. Cart A is positive 2. How fast is cart B moving towards Q at the instant when cart A is 5 feet from Q? So I'm looking for d B dt equals what when A equals 5. All right, and it should be a negative number because it's moving towards, it's decreasing that distance. So let's see. What can we come up with? Because really the only relationship that I have right now is this. So it'd be nice to relate A and B together. Well, by Pythagorean theorem, distance 1 should be the square root of A squared plus 12 squared. And d2 should be the square root of B squared plus 12 squared. So using that fact, plugging it in here and rewriting that, I would have root a squared plus 144 plus root b squared plus 144 equals 39. So now I have a relationship between a and b. So cool. That's really what I wanted. So at this point, it's going to seem annoying, kind of is, but we're ready to take our derivative. So if I do the derivative of my first, I have, let's see, 1 over 2 root a squared plus 144 times the derivative of the inside, which is 2a dt. So it'll be the same thing here. 1 over 2 root b squared plus 144 times 2b db dt equals 0. Let's see, I have a, don't have b, so how can I find b? Well, let's see, if a is 5, then that means this is the square root of 25 plus 144, which is 13. So if that's 13 and together they make 39, then this distance must be 26 at that instant, which means b is the square root of 26 squared minus 12 squared at that instant. Cool, now I have b. So I have 1 over 2 root, well here, let's go ahead and simplify some things first. All right, so 2 divided by 2 divided by 2, I can get rid of those. Same deal here, 2 divided by 2, I can get rid of those. And now I'm just going to plug in some numbers, because really I could subtract all of that over to the other side. So if I rewrite that as negative a dA dt over root a squared plus 144 equals b dB dt over root b squared plus 144. All right, and then we're just putting in numbers. A is 5, b is the square root of 26 squared minus 12 squared. I wonder if that's nice. Nope, definitely not nice. So I'm going to store that value as b. The way that I did that is the store button. Here I'm trying to hit it right now. So you see it in red on my calculator. Store. You can store whatever value you want as anything. So x right now on this calculator is 10. If I wanted x to be 5, I could say x, or 5, store it into x. Now x is 5 anytime that I want to use it. So now I can just put in the equation as is. So I'm going to do that. I did that with b. A is 5, so I'm going to put a as 5 so that I can just do, let's see, negative a times dA dt, which we know is 2. Right, so negative a2 divided by the square root of a squared plus 144. So that is the left side of my equation. Now for the right side, I need to multiply by the square root of b squared plus 144, and then divide that by b itself, so divided by b, so dB dt is negative 0.8671 feet per second, is how fast that is moving. These are probably the more involved problems that you will ever see. I would rather give you something more difficult in notes and walk you through it than I would rather you see on a test or a quiz. Okay, the last problem is a very good one that you can see on a test or a quiz. So we have Gravel is being dumped. Oh no, I look out, 3 minutes, I better hurry. Gravel is being dumped, very well, 35. Okay, whatever. I might not make it. So I have gravel being dumped. Yay, dumping a bunch of gravel, right? It's going to form in the ground. And as it forms, it's going to make a conical shape. And I think they even tell that to you anyways, right? It makes shape of a cone. They tell you that in the problem. At a rate of 30 feet cubed per minute. So my change in volume is increasing at 30 feet cubed per minute. And the pile of a cone whose base diameter and height are always equal. So 2 times the radius and the height are always equal, since the diameter is 2 times the radius. How fast is the height of the pile increasing when the pile is 10 feet high? So I'm talking about the volume, which the volume of a cone is 1/3 pi r squared h. And I want to find dh dt. How fast is the height changing? So dh dt. So I need to say then that the height is 2 radius, so v equals 1/3 pi. So the radius then is h over 2. H over 2 squared h, which means I have, what, 1/12 pi h to the 3rd power. Come on, we're out of 3, man. Now I can do the derivative, so dv dt equals, bring down that 3, so it's 3 over 12, 1/4 pi h squared dh dt, and then we can plug in some numbers. So dv dt is 30, positive 30, and then I need to multiply that by 4, I need to divide that by pi, and I need to divide it by the height squared, which is 100. So my change in the height over the change in time equals 0.3819 feet per minute. All right, hey, 47 minutes, look at that. Okay, that's really all I got for you guys today. Please let us know what questions we have, you have for us, and we will see y'all soon.